let me pause this and go ahead. Yeah, compare instructions. These are in chapter 11, and they're very, very similar. And this is what's nice about RS Logic 5000 is that the instructions themselves are very similar to the ones that are covered in the textbook. So if you the only big difference is tags, and we don't use data files, right? So we don't use those T4s and C5s and, and all those other things. So, we'll look at PLC, we'll look at bitwise logic, and we'll look at, so these are I've been threatening to run these off all the time. So this is the IEC data types. Now, the only data types that RS Logic 5000 uses is the only ones they use is they use small integers, they use integers, they use double integers, and they use a real number, a 32-bit real number. And then, of course, they allow to use string data. String data is ASCII codes. This is where we can send text information between different devices. And we all went over ASCII codes back in PLC 1, right? So use a compare instruction to energize an output instruction, cascade compare instructions. This is also a handout I want to go. Cascade compare instructions in series to set up an upper and lower limit in a control system. We did this so much that they finally added an instruction to do this, and we'll look at both of them. Use bitwise logic instructions. Use a jump instruction to skip over runs in a PLC ladder diagram. So we're going to start getting into our program control instructions. We'll use multiple jump instructions with multiple labels. So you can see that's two instructions, JMP and LBL. We'll discuss those. We're going to use compare instructions to develop what we call a conditional jump, which is pretty neat. And these guys have been around in every programming language that I have ever programmed in. And believe me, I programmed in quite a few. Use the master control relay instruction to halt the operation of a section of the PLC logic diagram. We usually use the MCR instruction for like emergency stops and stuff like that, so we can decide which instructions. Of course, this is the old scheme right here. This is the old scheme that we used in RS Logic 500. This is all the data files that were available to us. We also had an L data file that was added by the MicroLogic 1100, which was a long word, which was a 32-bit word, but it was L, so it would have been L9. Here's our data files. And the only ones that we're going to be concerned with, even though these are the IEC data type, is the CINT, the INT, and the DINT, and of course the 32-bit real number. Now, why can we have 32 bits here and get this range, and we can have 32 bits here and we get this range? Is that real numbers allow you to use scientific notation. So what we have is we have one bit, which is still the most significant bit that identifies the sign, and then we have a base, and then we have an exponent. So certain bits represents the base, and then certain bits represents the exponent. So that gives us the ability. Of course, y'all know as soon as you start using scientific notation, you're going to start rounding, right? You understand that, and you're not as accurate, but most of the time it's accurate enough. And characters, of course, characters are ASCII. Computer, of course, the computer only use, and we talked about this the other day, right? About the one's complement. We talked about two complements. I don't know why it's in here again. So, in binary, in the RS Logic 500, the way we identify the base of immediate addressing is we come up and we put a B at the end of the binary number. And we put an O at the end of the binary number, and I think that's actually a 0, guys. I need to come back and change that. I need to do it, man. Used to, they were so familiar for so long that we used to slash zeros so people wouldn't make mistakes. And then for a while, the printers would put a dot in the center of a 0 so you wouldn't confuse it with an O. Now we basically use the shape of the character to distinguish whether it's a 0 or an O. So an O is round, right? You understand? And a 0 is an elliptical circle. But it's still hard to distinguish. We can specify the base used by a tag. So let me bring up this. And we don't often use this until we get into our logic instructions, our ands and our ors. It's just so hard to deal with decimal numbering system. It's real hard to deal with that. So what we do is we can just go into your tag table, whether it's a controller tag. So what's the difference between a controller tag and a local tag? They're both in the field. So what we're going to do is we're going to get into, later on, we're going to get into task. We're going to get into, so we have a task, we have a main task. And this is what we call a circular task, which means it just sits there and runs all the time. What we're going to do in the next lecture is we're going to look at something called interrupts, where we can specify a task that automatically runs every 10 seconds. Well, every one of your tasks is going to have its own local tag table. And those would only be unique to that task. So right now we can't duplicate tags, but I can duplicate tags in another task because it's a completely different task, right? You understand? A controller tag is available to everybody. So no matter how many tasks you have running, then a controller tag would be available to all of the tasks that's running in your field. So make a difference. So controller tags they're universal tags, they're global tags, which means they're available to every task that's running in the PLC. A local tag is just available to what? To that task. So we'll look at tasks later on when we get into interrupts. We have a periodic task and we have event task and we have what we call a circular task or continuous task. The continuous task is indicated by this little arrow spinning right here. So continuous task means what? Yeah, it just runs. It just runs. Top to bottom, top to bottom, top to bottom, top to bottom. An event task would only run when an event occurs. A periodic task would only run at a time interval. So we'll say we want to run something every 10 milliseconds. And then it'll have a little clock on the side. I can't remember what the icon is for that. So global tasks, controller tags are global tags. They're available to all tasks that's running. And you can't repeat those anywhere. Except, you understand that. A local tag is available to that task. It won't be available later on when we set up another task. It will not be available inside that other task. It'll have its own tag table also. So when we go to edit inside the tag table that we're using, and then we go all the way over to the right here it says style. So right now it's set up for what? Decimal. I click on the little right hand side and I can make it display in what? Binary, octal, hexadecimal. So those bases that you already know. So when we get into logic instructions, bitwise logic instructions, odds are we're not going to do it in decimal. Because if we want to figure out the third bit on the left, if it's set or cleared, it's so hard to do in decimal, right? You understand what we're saying? So it's real easy to do to change the base. So to specify the base used by a tag address, we go to Edit Tag Table, select the Style column on the far right, and you can select the base. Everybody okay there? So these are the compare instructions we're going to look at. We're not going to look at the first one. I forgot to put what equal, and it's not covered in the textbook anyway. Equal to, greater than or equal to, greater than, less than or equal to, less than. Limits, which the book doesn't cover, but this was actually added with the Micrologic 1100 PLC, so it is supported by the RS Logic 500. This instruction is, so we'll go ahead and cover that, even though it's not covered in the textbook, because it takes the place of two instructions. Immediate addressing, this is when it shows us the addressing modes available. It's going to give us two things. Let's see if it's in here somewhere. So right here. So these are the instructions. So here it says we have two sources. We have source A and source B. And the data types that's available to us, we can use a cent, we can use an int, we can use a dent, or we can use a real number. The addressing mode available to us is we can either use immediate addressing or we can use tag addressing. So that's the two addressing modes. So this came right out of that general instruction manual that's so valuable for us to use, and I'm learning a ton of stuff out of it. So it means for source A, I can use either immediate addressing or I can use tag addressing. For source B, I can use immediate addressing or tag addressing, and we'll get into some limitations. But changing that numbering system over there, right? Changing the data type. So where do we change the data type at? So by default, we normally get what? Well, that's only for input. By default, we normally get dents. So counters, you get dents. So bills, this will get dents. But what we can do is over here. This is not a good example. I'll bring up my program and show you that. Right here. So it says data type. If I click, I'm in edit tags. So this is the only available blue. So here, this is a data type for a counter, right? Understand that. But we can change. Some of our instructions gives the ability to change from a dent to an int or a small integer, right? Y'all understand that? And this is where we would, if we had the ability to do it, this is where it would be. Counters are going to set up an array. So in RS Logic 500, we'd use what we call the R6 register, which was the flag register. And anytime we set up a counter, it automatically sets up an array. And what's an array? It's a group of consecutive addresses, right, that we can go through or index through real easy. So some of your instructions automatically set up an array. So counters set up a what? An array. What's in the array? We have an accumulator, which is a dent. We have the count down, count up, count down, count up, counter done, overflow, preset, and then the underflow. Underflow, yeah. So what is overflow and underflow counter? If you go over the range of the numbering system, right? So if we exceeded, that 2,147,000 something million, then positive numbers, it did what? It turned what? Negative, and you get an overflow. So, but these automatically sets up these arrays. So, and we'll look at that. These are called structured instructions, by the way, when we talk about RS Logic 500 and we start looking at the actual certification. Okay. I don't know where I'm at. So it means, so what we have on all our compare instructions, this will make a little sense when I go down to the compare instructions. So we have a source A and we have a source B. When we say equal to, what do you think that means?
Are they equal?
Are they equal? Yeah, if source A is equal to source B. Greater than. Is source A greater than source B? So when you say it, you say source A first. So first, A is first, and B would be second, right? You understand that? So what can source A be? Well, according to this, source A can be a cent, it could be a int, it could be a dent, or it could be a real number. And how would you say you could select the base, right, inside the table? Everybody understand that? Everybody okay? Source B could be a cent, it could be a int, it could be a dent. Y'all understand those? And then it could be using immediate and tag address. And one thing it don't tell you, is both of them can't be immediate addresses. Why is that?
And what?
Both of them can't be immediate addresses.
Could it be the same location?
Well, it'd either be always false or it'd be always true. So you say source A is 10 and it's source B and you put 10 in there is equal to source A, you put 10 in there and then source B, you put 5 in there, it would always be what? It would always be false. If you put 10 and 10, it would always be true. So that means if it was always be false, I would delete the wrong anyway. I wouldn't what? I wouldn't need it. If it's always true, I wouldn't what? I wouldn't need that instruction. I'd just make the wrong true all the time. You understand that? So both of them can be immediate, but source A could be a tag address, source B could be a tag address, source A could be immediate, source B could be a tag address, source A could be a tag address, and source B could be immediate, but both of them can't be a what? Both of them can't be immediate. Y'all understand immediate? Immediate means you type the number into source A. So that's immediate addressing. You type the number in there. Source tag means it gets that number from another location, right? From another memory location that we specify with a tag. So these are our compare instructions. Okay, so let's start off with equal to. The output is true if source A equals source B. Source A and source B can either be immediate or tag address, and both sources cannot use immediate address. You understand that? Odds are, I don't know, we might try, but it might not give you an error. Not equal to, the output is true if source A and source B are not equal to. So these are considered input instructions, so they'll go to the left, right? You understand that? And this would make this rung being true would be conditional. So if they're equal or greater than, then this rung would be false, right? I mean, if it's greater than, that would be not equal. Then it would be true, right? Everybody understand that? Yes or no? And then whatever you put out here would be true also. Of course, here we're just turning on a light. Less than. The output is true if the value of source A is less than the value of source B. Source A and source B can either use immediate or tag address, and both sources cannot use immediate address. Because it'd either be always false or always true. Right? Greater than, the output is true if the value of source A is greater than the value of source B. Source A and source B can be either immediate or tag address, and both sources cannot use immediate address. Less than or equal to. The output, and by the way, this gives you the little math equation.
Go back to that last slide.
Uh-huh.
You know, if the ERC was the code, was the GEC down there, greater than.
Yeah.
ERC.
No, you'd use this right there. That's the instruction. These are the actual instruction mnemonics right here. So these are the actual instructions right here. Yeah. So you okay? Okay. Yeah, so this is what you would type in. Or you'd pull in. You could type it in or you could pull it in.
You wouldn't use ERC,
you use GEQ for this one.
Okay.
GEQ.
It's not at the top. It's very top. It's not greater.
Oh, okay. I understand now. It took me a little while. Sorry for the confusion, guys. And of course, I've had to redo every one of these slides for 5,000, so we might run into another problem. I might have the wrong picture in here because everything here, let's see if I've got the other one. What's this one? I might not have a GET, but they're all basically the same. explanation. So this, I got a match, they match now, right? I understand the confusion now. I didn't read that. Less than or equal to, the output is true if source A is less than or equal to the value of source B. Of course, the next sentence is the same on all of them. Greater than or equal to. So this is right. So I do have it in there. The output is true if the value in source A is greater than or equal to the value in source B.
So the over what's supposed to be GRT? That was,
Yeah, I think so.
This should have been GET. So what I did is I pulled in the wrong picture. Yeah, like I said, guys, I've been working on this. So what did I do during my spring break?
you probably
Worked on this class, yeah. So the other one is supposed to be what? I'll have to come back. I'll come back and make that correction. So here's. I don't know how I got way off down here. So this right here is supposed to be. So this is supposed to be a what? It's supposed to be a G. What is the acronym? So we could have additional contacts inside this room. So if this is between 6 and 10, then it's going to increment the pound. It's going to increment the pound. So we use this so often that what they did is they established an instruction called the limit instruction. And like I said, this was available on the 1100 PLC. So this is the limit instruction where you put a 1. So when would this be available? So this is one instruction that replaced 2. So what we do is the lower limit, so I've got it set to 5. The upper limit, I have it set to 10. So this output would be true if it's what? Between what? This is that limit, yeah. It's going to be between the 6 and 9, right? Yeah. We okay? So this is the way we would do it now. You can still do it the old way, but this would be the way we would do it. So here we got a counter counting from 0 to 20. So we'll see how this is going to work. I'll go ahead and download it to my PLC. So counters, remember counters, you have to do what with them? You have to reset it, right? And what you do is you just give it the tag of the tag that you gave the counter. So if you bring up a counter instruction, it'll automatically build that array out there called that structured array for this account. So we're online. I'm using switch 0. Okay, so right now this says what? Greater than or less than. So if it's between what? Between 6 and 9, this run should go true. Here it says if it's equal to 10, this shunt run should go true. If it's greater than 10, this run should go true. So right now, none of the rungs are true. We'll start counting. I don't have a less than in here, guys. So here we come up, here's 8. So that's between them. So the output on this, on one not true. Here comes 10, right? Equal to 10. The output of this run went true, right? But we exceeded 9, so run 1 went false. Run 2 should go false because this is equal to it. So now it's not equal to it anymore. And now we're greater than 10 in the last run. So these are really powerful instructions. In programming, we use if. So the if this is equal to this or else this, and this is where we do the if else statement. If we're doing structured tests, by the way, that's the way we have to enter this in. But this is so much simpler using these graphical images. So any questions on these, guys? You okay? Well, it's going to stop. The preset. What happens on counters if you don't reset them? It keep count. So what I've done is the counter done. So here's counter _1. That's a tag dot done. So what's nice about this is you don't have to remember when you use a slash or when you use a dot. So it don't make any difference if you're using a bit instruction or if you're using a byte instruction or whatever. You just end it with a dot. So this says if it's done, it's going to reset the count. Or I can reset it manually using what? I can use a switch 1. So I've got this one I didn't give a tag. So this, I used the base tag here. I don't know why I didn't give it a tag. I couldn't give it one now while it's running. So yeah, if I come up here and hit 20, then it's going to reset and it's going to give us the first count. So this is what happens when you use that reset instruction on a counter. You missed a 0, right? It started counting the next count. Okay, so we're okay? So this is the limit instructions. It's the same. It's the same for all of them. I don't know why I brought it back up here because bitwise AND. A mask is a binary number used to make sure certain bits in the destination operand are 1s or 0s depending on the mask used. A decimal number system is not usually used for the mask instruction, even though the processor only understands binary. By default, RS logic displays numbers in decimal. To specify the data type for immediate addressing, you place what? For binary, you put what? To hashtag for, it used to be the number sign, but now we call it hashtag. Then 8, hashtag, give you octal, and then 16 would be 16 hashtags. This is for immediate addressing. To change the base in the tag table, you would go to what? Parameter local tags, or you can go to controller tags. I need to make sure I put that in. And then select the data type as what? Binary, octal, or hexadecimal. Everybody okay?
The math is used to confirm that it is the data type that I'm using on the math. And this math is binary number to make sure certain things in the destination.
Well, let's look at the instruction and see what happens first before and then this would make sense. So the first mask we'll look at is what we call the AND mask. So the data type could be sense, it could be int or dent or real numbers. Immediate or tag for source D. But we don't use immediate for both of them, right? You understand? Then the destination has got to be a tag over there. Okay. So here's the instructions, source A, source B, and source A. Well, what we're doing is called a bitwise, it's called a bitwise AND, which means, and it starts off, the default is a dent, which is a 32-bit number. Okay, you understand that? and I'm trying to and when we deal with our truth tables, nothing's in there is in decimal, right? You understand it's what? It's binary. So what we're saying, if I come up here and if I add 2,167 and 5,162, it's not going to make any sense because it's ones and zeros, right? You understand? So I'd have to get out a piece of paper and I would have to convert them over and I'd have to look and see what comes through. But what an AND math, we're dealing with two operands. And what's the truth table for an AND? A 0, 0 would give me a what? A 0, 0, and a 0, 0 would give me a 0, right? A 0, 1 would give me a 0. A 1, 0 would give me a 0. And a 1, 1 would give me a 1. So what happens is your math is going to be in source B. So what I would do is I would come over here, and this, now it makes sense. So this is an AND math. So source A came from value 1, it shows me here, and it's in what base? It's in binary. And it's bitwise, so we look at every bit. And now my math is this guy here, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0. Well, no matter what I have in source A, the destination is going to be a 0. Because what we're looking at, 0 and 0 is what? A 0. 0 and 0 is a what? 0. So over here, though, this math is an F. So over here, it came through what? Unaffected. So whatever's in source A came through into the destination. Over here, I strip this off. So what I'm doing with an AND math, I get the ability to make sure bits in my answer is a 0. What I want to pass through, I'll put a 1 in the math. What I want to strip off, I'll put a 0. But this would almost be impossible doing it in decimal, right? You understand? So here we're doing all of them in binary. I like hex because it don't display so big. Of course, I've been using the hexadecimal number system so long, I know the pattern, so it's probably easy to use that way. But this is an AND math. So what we do with an AND math is we make sure, for some reason out there, we're going to make sure that bits in my answer are a 0. If I want them to be a 0, I'll put a 0 in that position in the math. If I want it to come through, I'll put a 1 in that position in the math. When we say come through, it means if it's a 0, I get a 0. If it's a 1, I get a 1. Can y'all see what I'm talking about? So this right here, this guy right here, what did I do? This is the original number. What's my math? So a 0 and a 0, a 0 and a 0 would give me a 0. A 1 and a 0 would give me a 0. A 0 and a 0 would give me a 0. A 1 and a 0 would give me a 0. Over here, so what happened here, it came through unaffected, right? You understand? So this is what we do with math. With an AND math, we either make sure bits in our answer is what? 0. Any place I want to come through, I put a 1 in the math. Anytime I want to strip off, any bit I want to strip off, I put a 0 in the math. Well, I was working on bringing in this input. I was working on bringing in inputs over here. Well, the problem is I was using my first two. I was using my last two, my bits 15 and 14. I was using them as start and stop. So what would happen is that wasn't part of my number because I was using these to control the circuit. The rest of them I wanted to use the actual position of the switches. So all I wanted to do is I wanted to strip off in my answer I wanted to strip off the highest bit. You understand what I'm saying? Yeah. Because I was using these switches, and I didn't want these switches to affect the what? To affect the number. So what I wanted to do is I wanted to do what? Strip them off. So what math did I use? In hex, I used the what? I used the 0, 7, 0, 0. I'm sorry. 0, 7, and 8. So a 7 is a what? 0, 0. I want 0, 0, 1, 1. So that means when I flip these switches up here, this 15, this 14, that's what I was using to control the circuit. They would just what? They would just ignore it. So we'll show you in a minute how we can bring in a whole input port. Up until now, what we've been doing is we've been bringing in the individual bits, right? Our bit 0, bit 1, bit 2, bit 3. So we can bring in a whole input port if we want to. I'll show you how to do that. So that's one reason I did it. You know, whatever the reason, and that's a really good question. So what we do here is when I'm dealing with a number that I get from something, and I want to ignore this. So let's say I bring in a group of sensors, and I'm not concerned with this, what's going on with this sensor right here, then I could do what? I could strip it off by coming up with a mask. But when you come up with a mask, you're going to have to know binary. You're going to have to know binary. You're going to have to know hex. Right? You understand? And like I said, hexadecimal is easier for me, even though I don't know the difference between 7 and 3. It's easier for me because I've dealt with that number system so long, and it reduces the size of the block. So you can see these instructions get very, very big when you do with the binary numbers. So good question. Any more? But whatever, you're going to come up with a situation, I almost guarantee, where you're going to want to do what? You want to make sure no matter what comes in from that 16-bit input port or whatever, you want to make sure certain bits you're not concerned with. You're only concerned with certain bits. An OR mask will make sure bits in the destination are 1. So as on an OR, it's what? A 0 and a 0 is a 0. A 1 and a 1 is a 0. I mean, a 1 and a 1 is a 1. A 0, 1 is a 1, and a 1, 1 is a 1. You can see why it's called a bitwise, because we're doing it on each individual bit, right? Okay. And by default, when you create a compare instruction, by default, what data type do you think it uses? Uses DINS. So you've only got 7 inputs on your PLC. So what would you want to do with the other 24? You'd want to mask them off, right? You understand? If you were going to use your inputs to do something, well, how would you mask them off? You'd use an AND, right? You understand that? But an OR, we can make sure bits in there are set. No matter what I get in, if I want a bit to be set in the answer, I would put a 1 in my mask. A 1 in associated bits in the mask will result in a 1 in the destination address no matter what the state of the associated bit. A 0 in the associated bit position in the mask will allow the state of the associated bit in source A to come through to the destination.
Is the AND mask dedicated to soul?
Yeah, so what we do with an AND mask is we make sure bits in my answer are always 0. Right, you understand that? And ORs is 1. We make sure certain bits in our destination are 1. So that's the OR mask. So OR mask, what we can do, no matter what we get in from source A, no matter where it comes from, right? You understand that? No matter where it comes from, we can always make a bit inside that number of 1. So this is an OR. Here's our mask. We're using, looks like the same mask. So here, even though this is a 0, 1, 0, 1, all the bits are what? 1. Even though this is a 1, if I put zeros in an AND mask, OR mask, it comes through unaffected. They call this an inclusive OR mode. What about exclusive ORs? Exclusive ORs provides a means to determine if the associated bits in source A is the same as or different than the DAN binary. I proof these things 100 times and then when I use them. Of course, y'all probably do that in email too, you proof your email about 4 or 5 times and you send it out. And then you look at it and you say, gosh, dog it. An exclusive OR provides a means to determine if the associated bits in source A is the same or different than the associated bits in the OR mask in source B. The associated bits in the destination will be a 1 if the associated bits in source A and source B are different. So this is an exclusive OR. It will, the associated bit in the destination will be a 0 if the associated bits in source A and source B are the same. So here instead of, but what you're looking at is you're not looking at the whole thing. It's called bitwise because it's only done bits. So bit 15 would be OR to get bit 15 of source A, right? You understand that? Or these are 32 bits. So the number systems available to us in the addressing modes are exactly the same as the other one. So here, if they're different, so here they're different, and it comes to as a what? 1, right? Here they're the same, and it comes to as a what? 0. Here they're different, it comes to as a 1. Here they're the same, it comes to as a 0. We're not going to go, this is a pretty good example here. If we go through all 32 bits, we can see the same thing. So we're okay. A NOT complements or inverts all the bits in the source and places them in the specified destination. Can be placed at the output of an AND or exclusive OR instruction to simulate a what? An AND NOR or exclusive. So this is a NOT. I don't know why you'd use immediate address and you didn't NOT it, because you come up with the same answer all the time, even though it says it would be legal. If I was going to use the same number all the time, not unless I used it in 2 different places, that might be. But I can't understand why you'd use immediate addressing for the source. So this is a NOT. It's going to change the sign of the number, by the way, but it's not going to be a 2's complement number. So the number will become negative, but it won't be 2's complement. And a 2's complement, you have to take the 1's complement and add 1, or you have to subtract it from 0, or if you have to invert everything after the first 1 to get the 2's complement equivalent. So this is going to change the sign of the number, but it's just going to be inverted, right? Does that make sense? Yes, no? We do an AND mask a lot, so instead of me using an AND instruction, you can use this. It's called a moving mask. It don't tell you what mask it is, but it is an AND mask. So what we would do is we get the source, then we'd run it through our mask, and then we would store it in the destination. So this basically takes the place of 2 instructions. So this is move with mask. We looked at the move instruction already, but this is the second move instruction that's available. Are we okay? So this would be a move with mask, and here's my AND mask right here. By the way, the book is wrong. Not the book, the textbook only deals with 16-bit numbers. So RSLogic 500 only deals with words. The primary data type used by our numbers in RSLogic 5000 or Studio Designer is 32 bits, right? So it's a true 32-bit process. So move with mask, I got 3 1s over here, and notice it came through unaffected. Here my mask had 4 1s, it comes to 3 1s, it came through unaffected. Oh, it's got 4 1s here. The 1s come through, and so the 1s come through the mask, and then the 0s are what? A mask off, right? Everybody okay? So that's the logic. So this is logic. It's called bitwise because instead of doing it on, so if I do it with contacts, then if I do an and, then I'd have 4 or 5 contacts. This is going to take a whole, it's going to take a whole word or it's going to take a whole double word, right, to understand and do what? It's going to run it to a math. By default, it's going to use a then. But we can do what? We can specify smaller ones. The jump instruction used to jump over rungs can be jumped forward. You can jump forward or backwards. Always assign a number. Always assign. No, that's not right. Always, in our Logic 500, we use a U for U1, U2, and stuff like that. Here we're going to use a tag. So this is a lot easier to understand. Always assigned a base tag. Must have a label instruction with the same base tag. Can be used to formulate if-then else programming. So right now, when we run a program, we run it from what? Top to bottom, top to bottom, top to bottom, top to bottom. But what if we wanted to skip over some rows? We'd use a jump instruction. Or if we wanted to repeat a section a certain number of times, we could use a what? We could use a jump instruction. So we can jump forward or we can jump backwards. Jump, located in the program group, used to make PLC skip over rungs, always used in pairs. For every jump instruction, you gotta have a label. Everybody understand that? The label instruction that a jump sends the program to must have the same base tag. The base tag name is the jump. Jump instruction names can be repeated to cause the program to jump to the same label, address, and cannot be duplicated. So your jump instruction can't be duplicated, but you can use the same label multiple times. Program jumps can be forward or backwards. Program jumps can be conditional or unconditional. Always skips over a section of the program without meeting a predetermined condition. So we might even use this for troubleshooting. So if I've got a section of my program that I'm having problems with, and I just want it to not scan the other rungs, I just want it to scan these rungs, right? You understand? Then what we could do is we could just jump backwards until we figure out what's going on. So we use these for troubleshooting. We insert them, we take them out. We can set up a switch that we can cause a section to run and not run. It's pretty neat. And automatically inserted in PLC's machine learning program to jump from the end instruction. So the end instruction will always make, so we see this all the time. So when it sees the end instruction, that's just like a jump, but it's set to jump back to what? Back to run 0. That's what the end instruction does. With our jump instruction though, we can make it jump anywhere we want to within the program. So this is an example of a jump instruction. So what we have is we have the jump up in rung, I guess that's rung 1. And then we're jumping down. I left off the rung numbers, but I took that out of my program. When I input 1 is true, then it's going to jump over this rung right here.
Jumping over to what one?
Just one rung is all that's jumping over here. I think I've got this program. Can't find, no.
On the slide, for unconditional job. You have things that take and on the slide as well.
Yeah, I'll show y'all when I put the program in there. I can find it, guys. For some reason, I've lost my program. Okay, jump to it. The program in the book, I don't know if I've got that in there or not, but it's got a switch between, it calls it an unconditional jump, but then it's got a push button over on the left-hand side. Y'all understand what I'm saying? Y'all see that in your textbook? So, the one in the textbook, I don't know if I've got that. So the one in the textbook, if I've got this here, says this is an example of an unconditional jump. And what they do, or what the author does, he comes over here and he does this. And he assigns this to an input. Now what's wrong with that? And he's calling it an unconditional jump. What's the problem with this? That input has to be true. So this is not an unconditional jump, this is a conditional jump. If it was an unconditional jump, it would look like this. There wouldn't be anything between L1 and the jump instruction. So he says this is an example of an unconditional jump, and then he says if this switch is closed, the jump occurs. So yeah, the book is definitely wrong. So this would be an example of a conditional jump, right? You understand? Because what has to be done? Input's got to be closed, and if this input is closed, the jump occurs. So let's see if I've got this. If this is the right program. So yeah, it is. So how do I zoom? How do I zoom in so y'all can see it?
Yeah.
No, not control, alt Z. Shift alt Z to zoom in and just alt Z to zoom out, right? Okay, so we're going to download this. I know it's going to tell me for some reason mine every time I open a new program it wants to reconnect with the PLC, but I can live with that. Okay, so here we go. I'm gonna come up here and we'll just activate the jump. I don't know when I got the first one there. So switch 1. So here's output 0. No. Oh crap! This is the same one that's in the book. So this is the one I had to cut. What's wrong? Side. Some type of switch, sometimes some type of conditional instruction, sometimes like a compare instruction, some type of, timer done, something's going to be over there that determines when the jump occurs. Jump only occurs when predetermined conditions are met, activated by one or more input instructions, usually one or more contact or compare instructions. Can be used in many areas, So this is an example where we're doing a conditional jump. So the instruction in run 1, if it's equal to it, it'll jump over the next instruction, right? By the way, so over here on I'll go back to my other program. But over here, you sacrifice the memory bit for a point, it does what? Nothing. So this instruction has been available in programming languages for years. It's just that this is the first PLC that I found that actually supports it. So I'm gonna come over here for this this guy right here. I'm gonna go offline. Yeah, I'm gonna change this to a nope. This is called a no operation instruction, and it does exactly what it says it's going to do. What? Nothing. It's called a no op. Every programming language I've seen supports this instruction, but 500 did not do it. And I was going through some things, and I saw a sample program, and they used one of these in here. So this will work exactly the same way. It's just that a no op instruction basically does what? Nothing. And you don't sacrifice a memory bit for anything. This does not, it don't go true, it don't go false. It gives you the ability to put a instruction at a rung that basically does nothing. And that's what it says it says. It's a no op, right? No operation. So we can download this and it would work exactly the same. But here we're not using a bit instruction or internal. We're not using one of our internal ports. So this one says this is using a counter. As before, it only counts to 10. If it's equal to 5, it's going to jump over until it gets to 5. This instruction right here will be executed. As soon as it hits 5, it's not going to be executed anymore, right? You understand that? This says, okay, we're going to compare it to equal to 7. If it's equal to 7, it's going to jump over, turning on the wall. Turning on or off. This is one thing you got to understand. If the red light was on, and then you jump on it, it's going to stay what? It's going to stay on, because it's not updating the outputs anymore, right? So you have to remember that. We'll talk about that. The subroutine that they got in the book, we'll try to figure out how to take care of that, and we'll show y'all some of the problems. Master control reset instruction. This is also available in RS Logic 500. Does not replace the required external hardware e-stop circuit. So your e-stop circuit should be hardwired. Why is that? Has your phone ever locked up on you? Anybody had ever reset their phone? Well, anything that's running a program, we're dealing with ones and zeros, guys, and so all the instructions themselves are actually ones and zeros. All it takes is one bit to change. If one bit changes inside an instruction, that means we tell the processor to do something different. And so any type of EMF, any type of pulse, or anything that gets screwed up in the memory could cause programs to crash. The programs crash every once in a while. So I wouldn't want my e-stop button to depend on a program. For any really critical circuits, we still hardwire those. Right? You understand that? Okay. So we don't replace an e-stop circuit. The start circuit's still going to be hardwired, used in conjunction with a hardwired e-stop. So what we could do with an MCR instruction is we could disable, turn them off. Instructions, we could turn off output. So what we could do is if we hit an e-stop, we could automatically turn off outputs that were life-threatening, right? You understand? We could still keep the critical outputs on and turn off non-critical outputs without clearing them or doing anything. So very powerful instruction. Always used in pairs, an MCR output instruction. First MCR run conditioned while it's conditional, while the second MCR run must be unconditional. No control devices in L1 between L1 and MCR. Disable all non-retentive output between the pair when the MCR is false. So it's false. So what we'll do is the MCR is going to be, the first MCR is going to be true all the time. Run's going to be true unless something does what? Happen. Like you go over there and hit that e-stop button, and we can disable or turn off non-critical outputs. Inputs are still scanned and updated. Does not require an address. Additional NCR pairs cannot be within another NCR pair, which makes sense. You can't turn something off that's already turned off. Use to stop operation of control systems during a high priority system phase. The book says during a high voltage power outage. I don't know where they came up with that. Easily connected to a control power switch. Retentive latch outputs are not disabled, and this is not a detector. So this is an example of, by the way, these are examples of e-stop circuits. It uses a standard start-stop station. So we hit master reset, just like we do over there on our trainer, right? You understand that? It'll bring in our e-stop relay. We have e-stop buttons, and if we needed multiple e-stop buttons, we would just add them in series. Y'all understand this? Makes sense? Okay. So what we would do is we would come over here on our PLC and we bring an e-stop, one of the e-stop contacts, we would bring it into one of our inputs. And that would be the input that controls the NCR input. Everybody okay? Makes sense. This is another way we can do it. You see this also done when we come up here and we deliberately, this can only be done on certain PLCs. This is the 1100. What's nice about the 1100 is that we have a common for every output. It looks like we got a lot of outputs, but we only got 6. Because we got 6 connectors down there, but we only got 6 out. We got 12 connectors out there, but we only have 6 outputs. Because every one of them's got their own common. It uses relay outputs. What's the advantage of a PLC using relay outputs? So we can get DC outputs, we can get AC outputs, and we can get relay outputs. So what's the advantage of a relay? What advantage does a relay have over other control devices? So when you was over there in motor control, what was the voltage for the motor? What was the voltage that the motor ran up? 208. What did the relay, what did we use to energize the relay? 120, right? You understand? So I can have a DC relay. So what the advantage of a relay output is it don't care if you put, it's a contact. Contacts don't care if it's AC, it don't care if it's DC, it don't care. So an advantage of a PLC that has relay outputs is that they can switch AC, they can switch DC. You can switch 240 volts DC or you can switch 24 volts DC. You can switch, 120 volts AC or you can switch 26 volts AC. It don't care. And that's why if you look at these commons, I can't erase them, but the commons are labeled VAC, VDC. So relays don't care if you sync or source. So you can determine whether you sync or source. It depends on how you hook up the common, right? You understand? Relay switches have no idea. So normally when we wire wall switches, basic is to put the hot on the top and the switch, but you could switch it around, it would still what? It still work as a switch. So it don't care. It don't care if you put AC on it, it don't care if you put DC on it. So these are relay outputs. And the way the 1100 runs, it has a common for every output. So I can have this guy syncing, I can have this guy sourcing, so I could have this guy syncing, I could have this guy sourcing, I could have this running 26 volts AC, I could have this running 120 volts AC, and I could have this running, I don't know, right? What's the disadvantage of DC of relay output? So it seems like this would be the way to go, right? So what's the disadvantage? 2 things. Number 1 is electromechanical. What does that mean? And the next thing is what? They're slow. Because you have to energize the coil. The coil's got to switch a contact, right? You understand? So this is the 2 disadvantages. So I couldn't run a high-speed output. So this PLC right here has got, 2 high-speed outputs. I think it's got 2, at least 1. It can switch at 100 kilohertz. Might be more than that. Ain't no way in the world we're gonna switch a relay at what? 100 kilohertz. So here what we're doing is we're controlling the common. So my E stop is controlling the common. So what I do is I cut off the common. You should turn off all the outputs. Doesn't affect the input, it cuts off the what? The output. Or you might see it wired like this. So if I've got multiple commons, then I can allow some of the outputs to stay on, and then do what? Turn off some of them. So a lot of times we don't turn off all the outputs. We had cranes out at US Steel that we put these big old magnets on them, electromagnets, and they would clear out the scrap bins. And when something happened, you didn't want to lose the magnet, right? Because what would happen if it was up in the air? It'd drop. Yeah. So that was a critical. We used latch and relays on that. So keep the clear outputs active. This will take care of it. This is an MCR right here. I hope I have this program. So notice I'm using an examine if closed. So what would happen is my E stop, if everything was okay, then this guy would be closed, right? You understand? The MCR would be skipped over. So if the rung is true, the MCR is ignored. When the rung goes false, that's when it skips over rungs. And it skips over rungs between the what? Something's missing on this guy. Oh, yes. Here's my second MCR. Your second MCR needs to be non-conditional. And your first MCR needs to be what? Conditional. If this rung right here goes open, then it's going to skip over this guy right here. That guy, it's not going to skip over it. That output there would turn off, right? You understand? Let's see if I've got this program. I hope I can find it. I know I've got it somewhere because there it is. Questions? I just want to go lab, right?